Welcome, everybody. Today, I'm Cecil and Romy's over there. And, we are developers, musicians, engineers, and we work for a company called Quality SP. And somewhere last year, we took over development of this product called Scalar. And somewhere this year, we released the newer versions called Scalar 3. And Scalar is a procedural sequencer. And when I was walking around this conference trying to get people to join this talk, I was trying to explain what a procedural sequencer was. And they were, it couldn't really be explained in one or two sentences. And so I told them, join the talk and see how far we get. And when preparing this talk with Romy, we kind of try to figure out a way to explain it in a visual way. So in order to understand what a procedural sequencer is, we kind of need to understand what a normal sequencer or a classic sequencer is, and kind of get a lay of the lands of music software in general. What kind of music software do we have? What do we use? And we were brainstorming, and we had this great idea of trying to figure out this map of music software. So we fired up MS Paint and we came up with this diagram. Not the most amazing thing, but there's kind of two takeaways that we took from this and turned into something that's hopefully more understandable, right? So talking about interaction of music software as a user, from a user perspective, there's essentially two ways to distinguish. One, how do we interact with the music software? Secondly, what do we interact with? What are the elements we interact with? Put these in a diagram, and you will see at one end the what. So we're talking about, are we dealing with bare signals? Are we dealing with something more abstract like a note, or something even more abstract like a composition? And at the other end, the other axis, we're talking about how we interact. Do we move stuff around ourselves as a user? Are we tweaking parameters and have functions that move these things around for us? Or are we actually as a user programming these systems ourselves? And I guess the most tangible form of interaction is tape splicing, right? It's a very tangible way of dealing with bare signals directly. And in all honesty, like an audio editor is not much different. It's just more modern, right? But at the same time, you might be thinking of music notation software where you're dealing with notes. Something more abstract contains a little bit more musical information than bare signals. And something like virtual modular synths, audio racks, that is a little bit more procedural, but still deals with bare signals. And at the far end, we have a lot of programming languages out there that basically tackle any kind of abstraction that we want. Somewhere in between, there might be an effect that has a musical awareness, might be analyzing notes and such. And of course, our DAWs. The DAWs originate mostly from musical notation and audio editing. And nowadays, if you look at DAWs, they kind of try to take up the whole space. And it makes sense. It's an all-in-one package. You want to capture as much functionality as possible. Still, though, that leaves this area where developers maybe kind of seem to get lost. There's not that much music software out there where the primary means of interaction is something very high level and musically, like composition, harmonic narratives, chord progressions and such. Again, as a primary means of interaction. And this is something we want to talk about today. And it is something that is, I guess, kind of a hot topic, as there's another talk going on right now on procedural game audio. So check that out later, if we manage to convince you that this all makes sense. Going from classic sequencers that most of us use, to procedural sequencers where you're dealing with composition as the primary data element, means we need to kind of bridge that gap. Something is preventing developers from moving easily over that area. So this is kind of what we're trying to explain today. And in order to understand these classic sequencers, what's a good way? Well, we can look at the file formats, right? We can just look at how the file formats are structured to get kind of an idea about the data models underneath them. And if you're maybe 2 or 3 people in the audience that love reverse engineering, myself included, there's a couple of good references here and another talk from a couple of years ago that you might want to check out. So I've done a quick reverse engineering session for this talk where we kind of look at the file formats of four well-known sequencers. And what we can see there is, well, if we start with the project being an arrangement, and we assume that the project is the file, the next level of abstraction would be a track, right? Track containing instruments. We might then have clips, or items or regions as they're called differently. And in the end, we have the essential data element, the node, in all of these formats. Even if we look at more legacy formats and more eccentric formats, we see tracks and nodes always coming back. And the point here is that the nodes are the first-class citizens in all of these data models, right? So we have arrangements, tracks, clips, and nodes, and this is what I would call the classic data model, classic sequencer data model. And the point here is that as a user interacting with a classic sequencer, you're always expected to deal with nodes, to place nodes, to drag nodes, even if there's tools out there that help you with more abstract compositional things. You're always, in the end, putting down nodes. And it shows the origin of many DAWs as being in music notation software. And again, we're trying to get past that point towards something more procedural. So what does that mean? Okay, so instead of placing nodes, we level up. We take away the direct control over nodes and we place something else, something that contains a little bit more of harmony, musical information. Well, what's the next thing, the next layer of abstraction above nodes? That will be a chord. And if we let the user place chords instead of nodes and have some kind of system that then generates our nodes, which of course we need in the end, then we have the beginnings of procedural sequencer. Now, why does that work? Because a chord is simply just a group of notes played together, sustained notes. But with a very important distinction, it contains the basis of harmony. It contains musical information more so than individual notes. And that means we might have a chord of sustained notes, but we could also have arpeggiated notes or strumming notes. And these are all chords expressed in different ways. So looking at it, you're going from notes to notes still, and in the end we need notes. And we need something in between that probably does something with it. We call this a transform, and this, probably to most of you, this will look very familiar because in DSP, we also have these pipelines. Instead of transforms, we call them filters. And we have audio signals. Here we have nodes. Well, you could go from a note chord to an arpeggiated chord using a transform. But you might as well repeat that. You might as well transpose, go from arpeggiated notes to transposed arpeggiated notes and give them a time swing, for instance, and end up with pretty funky notes. And at the beginning, there's actually also a transform. And instead of inputting notes there, we can also input musical information there. So we have a generator transform that connects to an over-encompassing system now that we have. And this system has a little bit more, well, much more knowledge about music theory, tone scales, harmonic progressions and such. And we feed that information into the first transform. We generate the chord and we do all the rest. And just like with filters, you might have, for instance, a cutoff parameter or a resonance parameter. Well, for our transforms, we have more or less the same. We for a transpose, we might have a semitone parameter. And we can use that musical system to feed information into those parameters, which we call side channel. So we now have this kind of dependent graph of information flowing from an origin of music theory, ultimately into notes. And why does this matter? Well, it matters because let's say I was trying to compose a song, and I started out with my keys, my piano track. I have these chords laid out. I have my track chords and transforms generating notes. Now, let's say I wanted to add a bass, right? I would make another track, like in another sequencer. And there I would lay out now clips where I want to have notes, where I want the bass synths to play notes. I can now feed that information from my piano track coming from the chords into the clips, into the track of my bass synth, and generate musically relevant notes with this information flow. Could do the same with strings, for instance. Just feed information from the piano track into the strings and let it generate notes. Now, why is this interesting? Well, let's say I wanted to change something related to the chord progressions in my composition, or maybe something top level like a root note or a tone scale. All I would need to do is make that change, and then due to the information flow, all the notes that we ultimately need get regenerated automatically. So we're letting the computer do the work, and you can do crazy things with this. You might have a string track not playing notes while I'm playing notes on the piano, for instance. You can make it as crazy as you want to with this graph flow of information. Now, what are the downsides of such a system? Well, the arrangement needs to be deterministic. The transforms need to be deterministic. Why does that matter? Let's assume a random transform, for instance, right? We generate random velocities, random pitches. Okay, so far so good. Now, I change something, even if it's unrelated. The random transform gets asked to recalculate, and all of a sudden my notes and my velocities are going to be different. Imagine you're a user using this sequencer, and then you change the tiniest bit, and all of a sudden your bass synth notes are all jumbled up. It's not something you want to have. So you need to make sure that the transforms are deterministic. You could use a seed and hashing for that purpose. So if you give it the same input, it gives you the same output every time. That's not where we're done yet, though. If you use these techniques, and you might want to use sorting, for instance, and you're making a product that works on Mac and Windows. Some of you might know that runtime functions do not necessarily do the same thing on different platforms. So you need to make sure that it is deterministic across platforms. And you need to be aware of this when implementing all of it. And then the second problem is that we took away the direct control of the user to change notes deliberately. But as a musician, as a composer, you might want to tweak notes once you have your musical composition laid out. You might want to change a small thing. That's no longer possible. Now that's a problem because you lose the direct expressivity as a musician. So we need to figure out kind of a way to get back to that place where we can have happy accidents and these kind of things. And the upsides are, I think, very powerful. Again, if you change anything top level in your composition, like a tone scale or a progression or anything, everything automatically generates without you having to imagine. You have your old classic sequencer, you're going into tracks, you'd be like, oh, I want to change this chord progression around, but I have 10 tracks underneath it. You need to go through all of them. You might have a tool that does it for you, but the sequencer doesn't necessarily fundamentally do it for you. And this does do that. And that helps with experimenting, compositional experimentation and such, right? So let's put all of this to use. So I'm going to give it over to Romy now for a more in detail explanation.
Sure. Thank you. Uh, yeah, first, congratulations for making it to half of this talk. Thanks to Cecil for explaining like how to design such a sequencer and how it works. Now we're gonna see a little bit how to make music with that, and and we're gonna see how to make songs with it, because you can use it to make all sorts of music, but songs are easy and we know how to make them. So we're gonna be sequencing chords on a chord track, and we're gonna generate our arrangements entirely from that using transforms. And it's gonna look like this. So this is a view of Scalar 3, which is the product that inspired that talk. And we can see that we have chord progressions in the main tracks, and that we have other tracks with other instrument loaded, and everything, all the MIDI is auto-generated. And so far we've talked a lot about transforms. And if we want to get a little bit more into detail, we have to make a little bit of classification, like try to see what are those transforms. So since we are dealing with chords, like the first kind of transform that comes to mind is like what I call like voicing transforms, which are we're getting a chord as input, and we're going to voice it differently, either for targeting different instruments with different ranges, or just to change like the color that is expressed by an instrument. So it could be done through inversion, transposition, or different voice leading technique to have a smoother progression through a chord progression. So this is one end of the spectrum. And at the other end of the spectrum, we could say that we have like mangling transform, which are they're fed a sequence of notes which is organized in pitch and time, and it allows us to like repurpose this existing content into something new. Just having a downbeat becoming an upbeat makes some existing content acquire some new narrative. So rotation is an easy example, but we can, like, there's no limit to that. And like notes, they're just numbers, like time, position, and pitch. So we can apply all sorts of mathematical, simple mathematical transposition that are really useful, and that so it's like applying some degree of systematicness to something existing, and it's really powerful because in like classical composition or jazz or rock, there are a lot of people that have invented those techniques, and they are really easy to implement in a computer, not to replicate what they did in their music, but just to like use their influence to produce like to use it in other genres, like, such as pop, for example. So we have both ends of the spectrum. We have like voicing a chord, and we have mangling an existing sequence. Now we have to find how to generate what's the sequence, what's in the middle. So generating a musical idea, like what's the narrative. And we have to ask ourselves, what are songs made of? So this is an arrangement, and like the most basic form of like analyzing a song structure is the question answer structure, which is really simple. So we have two chord progressions, and the second one like ends in a different fashion than the first one. And so we can base our melody on this to have like an ascending movement at the end of the first one, and descending movement, for example, at the end of the second one. So that's like one level of narration and organization of time. But if we look at the other instruments, the bass, for example, retriggers every bar. So we have a retriggering pattern every bar, and the other track that could be a piano track, for example, it's retriggering every 2 bar. We are gonna use, we're gonna hear the same pattern that is transposed over the progression. And like the dynamic interaction between those patterns retriggering at different time units, it's what's gonna create, at least partially, a sense of narration. And so we're like, oh yeah, and also last bit about narration is like we can have different sequences at the end just to finish smoothly or loop over smoothly, on itself or just transition smoothly to the next pattern. But now it's like how to generate a melody, how to generate like piano comping or that kind of stuff. And it seems kind of easy like this because like it's held notes, little passages notes, like little ornaments here and there, and it's based on harmony. So it seems easy, but once you factor in like expressivity, velocity, micro timings, it's not that easy to convey a sense of narration in a simple phrase, like the hardest thing in music, right? So one thing we can do is we can leverage like the skills of the players and use curated content, which, if we think about it, in the last years has become more and more important. The availability of sample packs or preset packs or MIDI patterns pre-made has been greater. And it's a different sensibility to making music. It's not about creating stuff from scratch, but selecting, transforming, as we're talking about, and combining existing content into something new. And it's we don't think about it a lot when it comes to MIDI, but it's an approach that is very natural to a lot of people when talking about sampling. So yeah, if we take our transform stack, we get chords as inputs. We voice them in a way to give them a certain color. We can apply some recorded content, repurpose it to play with that chord. For that, we're going to transpose that phrase to the context. And after that, we can do anything we want. But so transposing is an important word here. And luckily for us, it's a really simple operation to do with a computer, where it's kind of difficult to do it live with an instrument. And it's just, we're moving notes, in pitch, as you can see. So it's a simple mapping of an ordered set of notes that are matched to degrees in a scale. So if I have an original riff in C major and I have only 5 notes, C, D, F, G, and B, I want to transpose that riff to G major. I just map the notes. The transposition is an easy operation, but it has a more complicated challenge, which is, okay, you're transposing to a scale, but how do you determine that scale? So let's say we have a nice bass line like this, very dynamic, and we have this chord progression below, and we want to adapt that bass line to that new context. So the first thing you can do is, this is badly displayed. We could transpose our bass line over each chord and deriving for each chord a scale and just transposing the bass line to that scale. But it's not that easy because you have to be really careful. It's not because something is minor chord, you're going to be transposing to minor scale, and it's a major chord, you're going to be transposing to major scale. Like in the D minor 7 example, it could be minor, it could be Dorian, all sorts of things. And a good example for that is like dominant chords, because dominant chords are tricky in their nature because they don't represent something by themselves, but they lead to something else. They're part of a cadence. So we can derive all sorts of scales for the jazz nerds here from that. And that's something to keep in mind, like the level of context analyzing you're going to have to do when you want to make composition tool can be high. All right, our bass line, we can also transpose it to the song scale. So C major, we're going to have a nice steady bass line over which the progression is going to unfold, interacting with something steady with something that is moving is a technique that is used a lot in rock music, for example. This works well because our progression is simple, but if we introduce differently voiced chords, like the C major we have on the bass here can be clashing with like the B that is playing on other instrument on the bass or something. So we might have to adapt here and there to avoid things like undesired tritones or semitone intervals. Yeah, so yeah, transposition is like the key part of a harmonic procedural sequencer like this. Yeah. Next thing I want to talk about is like this thing is great because it generates its own node, so you can just lay out chords, select patterns, and it's gonna generate the music for you. But as a user, sometimes you want to edit your notes because you're like this, you're an artist, so you want to retain some kind of control over it. Bad thing for you is like if we change a thing in the like upper level in the chords, in the transform parameters, now everything gets regenerated, your notes gets overridden, and suddenly not being able to composing like the masterpiece you had in mind. Too bad. So what we can do first about that is just okay, you're making an edit, you're on your own there. We're disconnecting you from the procedural sequencer. So what it means is we can have like procedural as a primary source of generating notes and having like the classical sequencer as a fallback. So that's one level. We can see we don't have transforms anymore, so we can reintroduce them because it's nice. But we have to be a little bit careful. So those transforms are disconnected from the chord and the rest of the arrangement, but we can still use them for little operations. But the user, they interact with those and they don't know what they're doing. Because what are those? This is a view of what's actually happening, but the model is actually like the chords, like the notes they've placed and the transform parameters. So for example, if we have a transform really simple that transpose everything one semitone down, you might see this C major 7 chord, but what's in the model is C sharp major 7 that is transposed one semitone down. So now if I want to add a note here, we have to be careful about being able to kind of invert that transform to be able to place the right note in the model. So we have to be careful about the mathematical properties of our transform, which is obvious in that case, but it's always valid when designing such a sequencer that is going to be imported at some point. And so if we want our system to be like predictable for the user, it's better if our transforms are bijective, which means the transform being a function that takes one set of nodes and make it into one set of nodes. It means like every element in the two sets have only, it has a 1-to-1 matching. So this is one way we can kind of preserve edits. It's all the way. But we can try to also not disconnect our sequence to the whole procedural sequencer when we make an edit. So let's say the user had this nice arpeggio, they wanted a D3 note instead of C3 here, and we change the inversion of the second chord. So now we have like two branches, right? And we have to figure out what's in there in the bottom right. And it seems simple, but it's not as simple. It's a little bit like version control problems where you have two branches and you want to merge them into a final result that makes sense and that don't break anything. And it's a little bit different because here we have like lots of knowledge about what the user just did. And we can make all sorts of assumptions to like encapsulate that simple operation, which is moving a note by one semitone, into something more meaningful to be able like to reconcile the two views. So did the user, did they move the notes a few semitones down? This is very vague. Did they move it to another octave? And that's the way it's like a really simple case because we can replicate that. Did they move it to another chord note, to one of the scale notes? So this defines like a list of priorities that we can check when looking at preserving the edits. And it's a really complicated topic, and there would be a lot to talk about, but it's a topic for another talk. So, so conclusion, yeah, Procedural is fun. Definitely try it, either as a user or as a developer. It's like, yeah, main pros are since all the changes are instantly propagated through the sequencer, it's really fast to try some ideas and to leverage existing content into other contexts. And so it allows for carefree experimentation. But yeah, in all the situations, the user is going to lose at least a little bit of direct control, making it, for you to make hard design decisions because you have to make assumptions or ask them what they wanted to do at each step, which is painful for them and for you. So, so yeah, I'll bring Cecill up again to.
Yeah, I guess is the audio working? Testing 1, 2. Yeah, there we go. I guess the point is we're not trying to stand over at the cliff's edge of procedural sequencers and be like, this is the next best thing. Goodbye, everybody else. We're trying to make that bridge. Like I started with this slide telling that we're trying to bridge the gap, and for the users, and our users are in fact somewhere on that bridge. We need to accommodate those classical node editing methods, those direct control methods with procedural methods. So that's what we try to present here, a bridge from the classic world to the procedural sequencer world. And I hope it was a little bit clear, and I hope everybody can now at least grab the concept of procedural sequencers a little bit more. So yeah, we're quite on time, I guess. I mean,